Hello friends, I am continuing my discussion on limits, fits and tolerances. So in my previous classes we have seen what is the importance of providing limits to a part, okay? And we have discussed about tolerances. We have discussed about unilateral tolerances and bilateral tolerances. So tolerance, as I mentioned, tolerance is equal to upper limit. Tolerance is equal to upper limit minus lower limit. And the important thing is tolerance is always a positive quantitative number. Tolerance is always a positive. Tolerance is always a positive quantitative number. Quantitative number. For example, if you take a shaft, of diameter 30 mm basic size plus 0.3 is the upper deviation plus 0.1 is the lower deviation. So now tolerance is equal to what is the upper limit here? It is equal to 30.3 mm. Lower limit is equal to 30.1 mm. So tolerance is equal to difference between this upper limit minus lower limit. It is equal to 30.3 minus 30.1 is equal to 0.2, which is greater than 0, which is a positive quantitative number. For example, if I take a situation of bilateral tolerances, let us take a shaft of diameter 30 plus 0.3 minus 0.2. It means it comes under bilateral tolerances. Upper limit is above the basic size, lower limit is below the basic size. So here what is the upper limit? It is equal to 30.3 mm. Lower limit is equal to 29.8 mm. Okay. So for example, if I represent this in the form of a figure, so if I consider this as basic size or zero line 30.3 mm. 30.3 mm is above the basic size, that is upper limit is equal to 30.3 mm, lower limit is equal to 29.8 mm. Okay, lower limit here corresponds to below the zero line, upper limit here corresponds to above the zero line or basic size. Okay, so here tolerance is equal to 30.3 minus 29.8. It is equal to 0.5, which is greater than 0, which is a positive quantitative number. For example, if you consider a shaft of diameter 30 minus 0.1 minus 0.2. Okay, so here it comes under unilateral tolerances. Here upper limit is equal to 29.9 mm, lower limit is equal to 29.8 mm. Both these limits lies below the basic size or zero line. Okay, so here the tolerance is equal to 29.9 minus 29.8. It is equal to 0.1, which is greater than 0, which is a positive quantitative number. Okay, so this is one of the important point to note. Okay, next we will discuss about fundamental deviations. This is one of the important topic to understand the limits, fits and tolerances completely. Next, once if we understand the fundamental deviations, we can go for design of limit gauges. Okay, so fundamental deviation. Deviation implies deviating from the basic size. Okay, basic size or zero line. Okay, so now what do you mean by fundamental deviation is, fundamental deviation decides the type of fit in the assembly. That is an important point. Okay, fundamental deviation decides the type of fit in the assembly. Okay, whether the mating parts have clearance fit or the interference fit or the transition fits depends upon the fundamental deviation. Okay, so and one more important point is fundamental deviation FD may be either the upper limit or lower limit. Fundamental deviation may be either the upper limit or lower limit, whichever nearer to the zero line. Okay, this is the important point to understand. Fundamental deviation may be either the upper limit or the lower limit, whichever nearer to the zero line. Okay, there are 25 fundamental deviations. How many fundamental deviations? 25. There are 25 fundamental deviations either for holes and shafts. Okay, there are 25 fundamental deviations for holes and shafts. They are the fundamental deviations for holes are represented by capital letters. The fundamental deviation for shafts are represented by small letters. They are capital A, B, C, D, E, F. Capital A, B, C, D, E, F, G, H, J, S, J, K, M, N, P, R, S, T, V, W, X, sorry, W will not be there, V, X, Y, Z, ZA, ZB, ZC. Okay, there are 25 fundamental deviations. In these fundamental deviations, I, L, O, Q, W are missing. Okay, let us check for it. There are 25 fundamental deviations. Whether I is there, I is not there. L is there, not there. O is there, it's not there. Q is there, it's not there. W is there, it's not there. Let us check for it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. A, B, C, D, E, F, G, H, J, S, J, K, M, N, P, Q, R, S, T, U. Here U is there. Okay. Capital U. Okay. Capital U, V, X, Y, Z, ZA, ZB, ZC. So there are 25 fundamental deviations for holes, and fundamental deviations for holes are represented by capital letters. Similarly for shafts, fundamental deviations are small a, small b, c, d, e, f, g, h, j, s, j, k, m, n, p, r, s, T, V, X, Y, Z, ZA, ZB, ZC. Okay. So these are the 25 fundamental deviations for holes. 25 fundamental deviations are for shafts. So what is the use of the fundamental deviation? It decides the type of fit in the assembly. Okay. So how to find the fundamental deviation? Fundamental deviation may be the upper limit of the hole or shaft or lower limit of the hole or shaft, whichever nearer to the basic size or zero line. Okay. Now let us understand the fundamental deviations more clearly by plotting the diagram. Okay. So if I take this line as a basic size or zero line. Okay. First I am drawing fundamental deviations for holes. Okay. Fundamental deviations for holes are represented by capital letters. Okay. Capital A hole will be having the largest fundamental deviation. Capital A hole will be having the largest fundamental deviation. Okay. Next comes the capital B hole. Okay. Next comes the capital C hole. As we go on further, the capital H hole the capital H hole lies on the basic size or zero line. Next is the JS. Next is the JS. Next is the J. Next is the K. Next is the K. Okay. So on up to the last one is the ZC hole. Okay. So see here, I have represented the fundamental deviation of A. The limits I have represented one with a straight line, and other limit I have represented with some form of a curve. Okay. So what is the meaning of it is for holes from fundamental deviation A to H, for holes from A to H has fundamental deviation is equal to, please here I have said fundamental deviation may be the upper limit or lower limit, whichever nearer to the basic size or zero line. So here if you look, this line corresponds to basic size or zero line. So this limit corresponds to lower limit. Okay. This limit corresponds to upper limit. So why I have for capital A hole, why I have represented upper limit with some form of a curve, you'll be understanding after some 5 minutes. So because we will be learning about what do you mean by tolerance grade. Then you can understand why I have represented the upper limit with some form of a curve and lower limit with a straight line, which is a fixed limit. Okay. So if you see, this limit is lower limit, this limit corresponds to upper limit. So out of these two limits, lower limit or lower deviation is nearer to the basic size or zero line. So for holes from capital A to H, A, B, C, D, E, F, G, H, J, S, J. Okay. So for holes from capital A to H, fundamental deviation is equal to lower limit, because lower limit is nearer to the basic size or zero line. Okay. For holes, if you look at the figure, JS comma J has no fundamental deviation. Okay. For holes from K to ZC, fundamental deviation is equal to, please see here, this line corresponds to basic size or zero line. This limit corresponds to upper limit, this limit corresponds to lower limit. Please look at here. Here I have represented upper limit with a straight continuous line, and lower limit I have represented in the form of curve, because here upper limit is fixed. It is the fundamental deviation. The lower limit can be varied by varying the tolerance grade. Okay, we will be looking what do you mean by tolerance grade and how many tolerance grades are there. Okay, so this is the upper deviation, or I want to say that upper limit is nearer to the basic size or zero line. So for holes from K to ZC, fundamental deviation is equal to upper limit. Okay, so this is the representation of fundamental deviation for holes. Similarly, we will see the how we represent the fundamental deviation for shafts. Okay, so fundamental deviations for shafts. Okay, so first I am drawing basic size or zero line. Okay, for a given basic size of a shaft, small a shaft will be having the largest amount of fundamental deviation. Okay, next comes the small b shaft, like that, so on. On the basic size or zero line, we'll be having the small h shaft. Okay, Similarly, this is the JS shaft. Next is the small j, so on up to ZC, ZC shaft. Okay. If you observe here, similarly as I discussed for the fundamental deviation for holes, here I am representing one limit with a solid line. I am representing other limit with some form of a curve. It implies that this limit which I have represented in form of a curve, this is the lower limit, this is the upper limit. This curve form indicates that lower limit can be varied by varying the tolerance grade, but upper limit is fixed. So if you take the small a shaft, out of the two limits, upper limit and lower limit, upper limit is nearer to the basic size or zero line. This corresponds to upper deviation for small a shaft. This corresponds to upper deviation for small b shaft. So this is the upper limit, this is the lower limit. Similarly here, this is the upper limit for small a shaft, this is the lower limit for the small a shaft. Okay. So we can conclude that for shafts from small a to h, fundamental deviation is equal to lower limit. Okay. For shafts from small k to ZC, for shafts from small k to ZC, fundamental deviation is equal to upper limit. Okay, because here this is upper limit, this is lower limit. Why upper limit is the fundamental deviation here? Because this limit is nearer to the basic size or zero line. If you take the K shaft, small k shaft, this is the lower limit, this is the upper limit. Lower limit is nearer to the zero line. Okay. So this is the representation of 25 fundamental deviations for shafts. Okay. I want to say one important point. For a given basic size, of a hole or shaft, we have how many fundamental deviations? We have 25 fundamental deviations. Okay. So having understood the meaning concept of fundamental deviations, now we will discuss about tolerance grades, international tolerance grades, that is IT grades. Okay. For a given basic size, of hole or shaft, we have 25 fundamental deviations. Okay. For every fundamental deviation, we have 18 grades. We have 18 grades of tolerances. For every fundamental deviation, we have 18 grades of tolerances. The tolerance grade denotes the accuracy of manufacture. Okay. So what are the 18 grades of tolerances? They are IT01. Okay, IT0, IT1, IT2, so on up to IT16. As the tolerance grade increases, tolerance value increases. Okay, as tolerance grade increases from IT01 to IT0, IT1, IT2 up to IT16, the tolerance value increases. Okay. So what I want to focus is, for every fundamental deviation we consider, we have 18 grades of tolerances. Okay. Let us represent these 18 grades of tolerances in the form of a figure, so that the understanding can be made clear. So for example, For example, if I consider this is the basic size or zero line, okay. If I consider capital A hole, in the previous diagram I have mentioned that upper limit for capital A hole is represented in the form of a curve. It implies that upper limit can be varied, keeping the lower limit fixed. I am keeping the lower limit fixed because the lower limit for capital A hole is fundamental deviation. Okay, the fundamental deviation value is always fixed. Keeping the fundamental deviation fixed, by applying the tolerance grade, you can vary the upper limit. Okay, so if I take this as capital A hole, if I take this as capital A hole, this as IT01. Okay, this is IT0. Okay, this is IT1, so on. This is IT16. Okay, so here the lower limit, which is the fundamental deviation, is fixed. Okay, as the tolerance grade increases, the upper limit is getting changed. Okay, the difference of the upper limit and the lower limit is the tolerance value. Okay, the difference of the upper limit and the lower limit is the tolerance value. Okay, so as the tolerance grade is getting increased, the tolerance value is increased. Okay, so we'll be seeing further the importance of these tolerance grades in my next lecture. Okay, thank you.